Hello everyone, this is part 4 of section 2.3, techniques for computing limits. In this part, we're going to see the squeeze theorem and how to use it to compute limits of functions that regularly we wouldn't be able to do. So imagine we have information about the limit of two functions that are bounding a third function. So a situation like I'm describing here, essentially I want to know what is the limit of g of x at certain point A. But g of x is very difficult to compute, or I don't know the formula. There can be many situations that prompts me to use this. But what I know is that the function g of x is bigger than certain function f of x and is bigger than certain function h of x. So as you see, if I know that nearby that point, I can have that situation is going to happen. Then what I can do is I can approximate the limit of g of x if the limit of f and the limit of h are going to coincide in both sides. So notice by the left side they're coinciding, by the right side they're coinciding. So that means that I can say, well, if whatever is in top and bottom of the function g is going to a certain number, then it makes sense that g also goes towards that number. Okay? So the definition of the squeeze theorem will be: assume that you have f and g functions, f, g, and h functions that satisfy that f is less than g, less than h for values of x near a point A, except possibly maybe at the point A. And we have information about the strings. We have the information that limit when x goes to A of f of x is the same that limit when x goes to A of h of x, and is going to be the number L. So that implies that the limit when x goes to A of g of x is also going to be L. Let's see an example of this. Consider the function x squared sine of 1 over x. This function is very difficult to manage, especially when we're talking about 0, because when I plug 0 here, notice that that's a discontinuity. 1 over 0, it doesn't get a good value. 1 over x goes to infinity or to minus infinity, depending on where am I approaching it. And so sine of 1 over x is going to be undefined. However, I do know the sine is a function that is between 1 and 1. So it doesn't matter what happens, it should be a value close to 0. Now, what we can see from this situation is that the function x squared sine of 1 over x is going to be bounded by two functions. It's going to be bigger than minus x squared, and it's going to be smaller than x squared. So it's going to be bounded by that. Why is that happening? Well, that's happening because in particular we do have that the sine of x is a function between minus 1 and 1. And so sine of 1 over x is not going to be an exception. That also holds true for that. Okay? And so I can multiply by minus x squared, by x squared. And so in doing that, I'm going to get the following inequality. Now, using the squeeze theorem, notice that I can see that the limit when x goes to 0 of minus x squared is the same that the limit when x goes to 0 of x squared, and it's going to be 0. By the squeeze theorem, that implies that the limit when x goes to 0 of x squared sine of 1 over x is 0. So notice that I don't need information about the function in the middle. I can just use the information about the bounding functions. Okay? Now, of course, part of the difficulty of this is actually set up the situation of one function bounding the others. Another example of this will be consider the function cosine of x. So it turns out that the function cosine of x is less than 1. We know that. Cosine of x is also between minus 1 and 1. However, that's not going to work here. We want to measure also around around 0. So although we can say, well, sine of x is between minus absolute value of x and absolute value of x, between minus pi half and pi half. If I'm going to work with the cosine of x, notice that this is the black function here. I need different functions to bound it. So I can bound the top with 1, but I'm not going to be able to bound the bottom easily. So I need something that goes below. So that's why I use the function, I use 1 minus the absolute value of x. Notice that the minus the absolute value of x is this blue function, just like this. So if I need something that it gets closer to this, what I do is I just add 1, so the function is going to go up 1 unit. And so now notice that this function cosine of x is now bounded by a function above and a function below close to 0. So with this, in both cases, we'll be able to find the limit when x goes to 0 by the squeeze theorem. With the sine, by using just the absolute values, and with the cosine by using 1 minus absolute value of x and the function 1. Now let's take a look at a different example. In here, we're going to introduce one of the new limits, which is limit when x goes to infinity. This is going to be a topic of the next coming sections, but we're going to use it now for an example of the squeeze theorem. Notice that we have a very complicated limit. And if x is going to infinity, this top looks like it's going to infinity, and the bottom also looks like it's going to infinity. So this is, again, very similar to the 0 over 0 form. This is an undetermined form. So we should find an alternative way of finding the limit that just plugging in. So what we're going to do is we're going to start with the assumptions. At this point, you guys know the basic idea. If I have a trigonometric function, then I can use the normal bounds. So sine of x is between minus 1 and 1. Turns out that at the same because of the same reasons, sine cube is also going to be between minus 1 and 1. Just cube everything. Minus 1 cube is minus 1. 1 cube is 1. And in the same fashion, cosine is also between minus 1 and 1. So if I add this to inequalities here, I'm going to have that minus 2 is smaller than cosine of x plus sine cube of x less than 2. So I added this to inequalities. And now I have an inequality for the top. So notice now I can multiply this by 2x on both sides. And so if I do that, I'm going to get 4x sine cube of x, 4x. So far so good. I only need the bottom, so I can divide by this x to the 4x minus 6. And in here, I'm going to have the full function now. And so I manage now to bound the function between two other functions. Now, what we care is for the squeeze theorem is, are we getting the same results when we're going to infinity? Turns out that that indeed is the case. If I take the limit when x goes to infinity of this is going to be 0, which is going to be the same that the limit when x goes to infinity of this. Essentially what is happening is that this is going to grow so much more faster than whatever is in the top, and so that's why this is going to go to 0. More explanation on this in the comment section. But now, because we had this, then by a squeeze theorem, we have that the limit of whatever is in the middle is actually going to 0 as well. And that is the end of the example.